All right, guys, part 3 of our probabilities and research lecture. This one's about hypothesis testing and inferential statistics. And yes, I know you're probably saying the last one's about that. Yes, they were. This one is still about that. This one is also going to introduce hypotheses and the hypothesis testing aspect of that. And so this graphic that says I am what is, the default, the status quo, I am already accepted, can only be rejected. The burden of proof is on the alternative. I am the null hypothesis. This is what we're going to talk about. That's just kind of a cryptic way of presenting it, but it basically is about that. Now, to get there, let's refresh a little bit. First of all, why is the word variable spelled variable? It's something that has the ability to take on multiple values. That means a value that always is the same is not a variable. It is a constant. Remember this when we talk about independent variables. Independent variables will describe the different levels of that variable of interest that's being manipulated in a study. So we've talked a lot about a caffeine experiment where we look at memory. The amount of caffeine someone consumes, a lot or a little, are the levels of that independent variable. Caffeine itself is not an independent variable because the caffeine group doesn't vary. It's the group that all got a lot of caffeine. They're stuck at that point on the scale. The other people are at this other point on that scale, this nominal categorical scale that we call the independent variable. And so in this case, we're just trying to remind ourselves that this is all part of one variable. We're simply looking to see whether or not the individuals that fall at each level of that individual variable, that independent variable, then perform differently in something we can observe or measure. So if the independent variable is what we're manipulating, it's what creates our groups, our experimental or control groups, right? Then the dependent variable is what we're observing or what we're measuring. This means when we craft our hypothesis or our hypotheses, what we're doing is saying how we believe the independent variable will have an effect upon the dependent variable, right? The dependent variable is dependent upon your assignment to a group in the independent variable. That's why it's called dependent. So let's formalize that a little bit more because it's not just as straightforward as making a hypothesis. Right? We did say before it has to be a specific prediction. It's not a question. But there's a little bit more nuance to it even than that. So first, let's think of the most basic experiment. Terms you've probably heard before, but at least in the context of this class, we've not really talked about from a definitional standpoint. Control group and experimental group. Traditionally speaking, you would say the control group is the group that matches the experimental group in all basic ways, except it doesn't get the experimental manipulation. Jakey here is my puppy and has nothing to do with the control group, but is cute.
What is a key?
So the control group in our example of caffeine and memory would be the group that didn't receive caffeine. They're just the same as the other group in all basic composition, right? Demographics and other sorts of things. But they didn't get the caffeine, the other group did. So if they're the control group, then the experimental group is the one that gets the treatment, gets the manipulation, gets the caffeine in this case. And so our hypothesis would be that the experimental group would, on average, have better memory for a word list than the control group, because we believe that caffeine, I believe that caffeine, would lead to an increase in encoding and retrieval of those words, and thus better memory performance on average. But I also said in the last lecture that when we do hypothesis testing, we don't get to test our own hypotheses. We're testing the hypothesis that nothing is going on, right? So in this example, that caffeine has no effect whatsoever on memory. We want to see whether or not the data we collect in our experiment fits that hypothesis, what we call the null hypothesis. Now look, I'm a memory researcher. I'm all about mnemonics and things that help you remember things. So I like the mnemonic here that the null hypothesis is the dull hypothesis. If I personally, as a researcher, believe that caffeine affects memory, I'm probably excited to go run this experiment and see if I find it. The alternative that says caffeine doesn't affect memory, that is dull, that is boring to me. But that is the one that we are going to test. And if we find any evidence that the null hypothesis is true, then we're going to say, hey, it might in fact be the case that there's no relationship between caffeine and memory. But if we can rule out the null hypothesis, and we know that our groups were basically equal in everything except for our independent variable, then that allows us to reject the null hypothesis and say, no, it's definitely not the case that nothing is going on. In fact, we might say that we have support for our alternative hypothesis. Now, the alternative hypothesis doesn't have a really cool phonetic mnemonic there. In fact, it has synonyms. Some people call it the researcher hypothesis. Some people call it the experimental hypothesis. Alternative is the most accepted term. The way I like to think of the alternative hypothesis is as the sexy hypothesis. If the null hypothesis is the dull one that says nothing's going on in your study, then the sexy one that gets you excited, makes you want to read the research and conduct the experiment, that's your hypothesis. That's you believing that caffeine affects memory, not that caffeine has no effect. We're going to try and set up the situation in our experiment where if we find any evidence that these groups differ, one performs better than the other, it has to be because the only thing between them that differed was the independent variable, that it's because of that difference, because of that difference in caffeine. Right? And so we're always trying to rule out the null hypothesis. An example. We all have this situation. You do laundry. You swear when you put your laundry into the laundry basket, you put in 2 socks. But when you get it back out, for some reason, you have only your right socks. And the left socks are gone, as if you could know the left from the right. But one of those socks is missing. What is one hypothesis for what could have happened? I'd guess at various ages where I have asked my children this question, they may have come up with this alternative hypothesis, their sexy hypothesis, the one they believe to be the case. Extraterrestrial beings have transported themselves into my house in order to steal my socks dead. That is what happened to them. Okay, so that's their belief. What's the null hypothesis then? The null hypothesis says aliens are not to blame. There is some other explanation for the disappearing socks. There's no relationship, in other words, between aliens and the disappearance of the socks. So now what we have to do as researchers is test the null hypothesis. Can we find any evidence that something else could be to blame for the disappearing socks? Well, as it turns out, no, we can't. So we have to reject the null hypothesis and tentatively conclude that aliens are stealing all of our left socks. That is, with the joking part aside, the essential philosophy behind hypothesis testing, right? We construct this belief about how we think this variable will affect this variable. We always have, of course, in our back pocket that nothing could be going on between these two variables. And so we're going to take the safe position and try and find evidence for the idea that nothing is going on. And when we can overwhelmingly reject that idea, because what we would expect to see in a normal chance situation, we saw something so different from chance, well, then we can reject the null hypothesis, and that's the term we use, and we can then accept or support our alternative research hypothesis. Now, in a situation where you don't find that evidence, these groups look to be essentially the same. The way they each performed is well within what we would consider the bounds of normal variability according to probability. Well, if that's the case, then we're going to fail to reject that null hypothesis, right? And we're going to say that it's entirely possible that nothing is going on whatsoever. Now, this is all based on probability. Now, I don't need to get into the p equals 0.05. You may have heard of that terminology in the past. It involves a 5% probability that we're making an error whenever we make a conclusion. We'll get into how that plays out specifically in hypothesis testing later, but for now that simply means that scientists never prove anything because we're always making a conclusion based on some probability. Here's how far we would expect these two groups to be different on a normal range of probability. When they get out to the very tails, where we know that's really unlikely to be that different from one another, that's when we start to say it's likely the case that the null hypothesis is false, and we reject it. So it's all based on probability, which means there's always a chance that you're wrong, which, again, is why we don't prove. But also means that in every scenario, we have 2 possible errors and 2 possible correct decisions. All right, so I'll give you a table here in a second to unpack them, but the types of statistical errors we can commit are called type 1 and type 2. Sometimes they're also referred to as sins of commission or sins of omission, but I like the type 1, type 2 terminology because it's a little more accepted. The type 1 error occurs when we have rejected the null hypothesis, okay? But the null hypothesis is correct. So if you believe that you have found data that says these groups perform differently from the way we would expect them to perform if the null were true, then we reject it and we find support for our research hypothesis. But it's possible that that was just a fluke occurrence, and those groups look differently, but if we were to study them again, they never perform differently again moving forward. And in fact, it was just that one chance occurrence that happened. That can be the case, and in this case you make a type 1 error because you believe you have found evidence for your hypothesis, when in fact that's not the reality in the world around you, right? This can be a problem because if I found evidence, let's say, that a particular vaccine was good at stopping severe infection from a flu or other viral strain, but it turned out that that was just a fluke in my sample, well, then I'd provide that vaccine to a whole bunch of people thinking it was protecting them. They might change their behavior. They might spread the disease out there. That could be an issue. That would be one thing that could happen in a type 1 error. We could do this in psychology as well. I might conclude that caffeine affects memory because in my experiment, it looked like these two groups were different enough that I could reject the null hypothesis and say that caffeine had an effect on memory. But what if that's not really the case? Caffeine has no effect on memory. Now, that's a much lower sort of negative outcome in this scenario than the prior one, but there still is a negative error that occurs here. I now tell individuals that caffeine affects memory. They believe it does. They start drinking coffee before exams and drinking coffee before class, and it turns out it's having no effect at all, or maybe worse, it's having a negative effect on performance that I didn't see in my experiment because I didn't look at that behavior. Right? So type 1 errors can be a problem. And the degree to which a type 1 error is an issue, like a huge issue, as it might be in the sort of viral case that I discussed first, a lesser issue in the memory case, the caffeine case, as I discussed in the latter, thankfully we have control over our type 1 errors. Because when we set that p equals 0.05 value I keep alluding to, that I promise we will discuss more about in the future, that 5% is up to us. We can do 10%, we can do 2%, and that 5% is the risk of a type 1 error. So if we think it's important to avoid a type 1 error in that particular scenario, we can adjust that, and we can instead take a 1% or a 1,000th%, right, type 1 error, risk of a type 1 error. The other case could also happen where the null hypothesis is false. It does actually occur in the real world. The vaccine does in fact cure from that virus. Caffeine does in fact improve memory. But in our experiment, we didn't find evidence of it. It could be that we just didn't run the study right, or our participants randomly didn't perform differently that day, or any number of factors could have affected that outcome. But we conclude that the null hypothesis is true, right? We fail to reject it and say that caffeine doesn't affect memory. This vaccine doesn't affect the virus. But the null was false. It did actually affect the virus. It did actually affect memory, right, in that case. So type 1 and type 2 errors. Now, we have some control over our type 2 error as well. So we refer to p equals 0.05 as alpha. Again, all stuff I'm going to repeat, so it's not heavily important that you remember the p equals 0.05 stuff at this point. We refer to that as alpha. The type 1 error, the risk of a type 1 error, is our alpha rate. The risk of a type 2 error is our beta rate. The one thing about type 2 error, we can reduce our probability of having a type 2 error by collecting more participants. If we have more observations of a behavior, then we'll be less likely to make that type 2 error. Okay? So one real quick, I guess, contextualized example to help you think about type 1, type 2 errors. Let's say we have a possible 2 states of the world out there, right? And these are the true, actual states of the world. In world A, you are pregnant. In world B, you are not pregnant. Okay? 2 possible outcomes, right? It's a Schrodinger's cat experiment here. You take a pregnancy test. 2 possible outcomes. Let's ignore all the possible outcomes in the middle where it says the test is unclear or it made an error and you should buy another test. Let's just pretend it's 2 possible outcomes. It says you're pregnant. It says you're not pregnant. It's just like an experiment. You have the true state of the world, your hypothesis. How do those interact, right? How do your conclusion and hypothesis interact with the true world? In scenario A, you're pregnant. The test says you're pregnant. You say, okay, it reflected me accurately. Hopefully that's good news for you. And you move on. You have this positive life and hopefully a cute little baby, right? In the other state of the world, that's a correct decision. You're not actually pregnant. The test says you're not actually pregnant. You go, whew, I can wait a little bit longer, or damn, guess Time to climb back on that horse and try again, right? In either of these two, you would consider these correct decisions. What about the errors? The type 1 error. The actual reality is that you're not pregnant. Your test says you are pregnant. What do? Well, you might change some lifestyle stuff. You might stop drinking if you drink. You might stop smoking if you smoke. You might change a few other things. What's the worst case scenario here? Turns out you're not pregnant. The test was wrong, and you got a little bit healthier. In this particular context, the type 1 error is not all that big of a risk, and so we can accept a test that has a reasonable type 1 error rate, a false positive that'll say you're pregnant more often than you're actually pregnant. But what about the alternative situation? You're actually pregnant. You take the test, and it says, you're not pregnant. So you say, hell yeah, I am still going to that bachelorette party. I'm going to Cedar Point tomorrow. I'm going to party like crazy, and just for the hell of it, I'm going to take a tumble down the stairs. No, those would be terrible for that unborn baby, so don't do that, but you wouldn't know. The test gave you the wrong information, right? So again, the particular context is going to determine the gravity of the type 1, type 2 error. It's up to you as the researcher to determine that and then take appropriate steps like changing your type 1 error rate, your alpha rate, or increasing observations to avoid that type 2 error. So 3 videos for 1 lecture, starting with risks and rewards of sampling, random sampling, convenience sampling, all those things about bias samples, and then more about cluster and volunteer and stratified sampling. We talked about how after you get the sample, you then want random assignment so that you don't have any bias in what individuals end up in which groups of your experiment, right? Helps for replication, confidence in findings. Then we sort of moved into a theoretical view of probability. What does it mean? How does probability work? Why are we so terrible at it? And have confirmation bias and gambler's fallacy sort of phenomenon, illusory correlation, superstition, groupthink, and really basically determine that we really suck at it, and so we have to find a different way of looking at it, an objective way. Here is what probability says should occur within some reasonable level of chance. Let's say 95% of the time, this is what we think would occur. If what occurs is something that we think would only occur 5% of the time, then maybe something interesting's going on. And it's not that the null hypothesis is true, and instead that my sexy research alternative hypothesis is in fact the case, and aliens are stealing our left socks, right? So that pretty much finished off that sort of probability theory and hypothesis testing stuff with the last little bit on type 1 versus type 2 errors. So make sure you know how to identify a type 1 versus a type 2 error. If I were to give you a particular example, be able to think about it in your own mind. There might not be a clear right or wrong answer about whether type 1 or type 2 errors would be the more grave one in that scenario. Okay? If you can do all that, and you can do everything else we talked about in the previous 3 or so lectures, then you are ready for the exam. Make sure you know how to do your math, and make sure you know how to talk about these sorts of issues so that you can handle the multiple choice as well as the short answer sections that you'll encounter on there. All right, that's it. Cheers. That is the end.